is about Griffiths 1.3.5, talking about the fundamental theorem for curls. So just like gradients and divergences, there's also a fundamental theorem for curls. And that states that if I take all of the curl of a vector field along an entire surface and add that up, that equals the path integral of that vector field along the perimeter of that surface. All right, so this path integral on the right is a closed path. It's just a surface integral on the left side. Okay, so what does this mean? All right, so let's go ahead and imagine some arbitrary surface. I'm going to draw it flat because it makes it easier for me to draw, but it doesn't need to be. And we look at the curl of in each little piece of my surface, right? Each little dA. All right, so I imagine that I have some curl here, some vector fields curling here. All right, I'm not going to draw all of them. I'll draw them bigger so I don't have to draw as many. Maybe they're not all going in the same direction. Maybe they are, who knows? But you may notice that internally, there's a curl of my field going this direction, while adjacent to that, there is a curl going in the opposite direction. All right. If your dAs are small enough, those two contributions will cancel each other. All right, and all you're going to be left with is the net rotation of your vector field on the outside. So you add up all of your components of your curls, and that is just your vector field evaluated along this path. All right. This is called Stokes' theorem. We're going to use this quite a bit as well. Just a note though, this surface can be any surface as long as you have a bounded path. All right, so if I imagine something that looks kind of like a balloon, I could have a traditional surface like this in 2D, where this is my perimeter and my area is just, filling all space between there. Or I could have something that looks like a balloon, or I have a bottleneck right here. All right, this is my perimeter, and I have some surface in 3D space. Okay, where now the area that I would integrate over would be this space here, not the open neck here. But I still could integrate my path integral over this small perimeter and this small loop that encloses this path. All right, so we can test it like we have in the past. We can go ahead and take the curl of our vector field, and we need to define an area over this surface, and we need to define a perimeter. Right. So example 1.11 in your book picks the surface in the YZ plane, YZX. It's this surface that they choose, and it is the path going around that surface in a counterclockwise fashion. So let's go ahead and do that. So the field that exists here is said to be 2xz plus 3y squared in the y hat direction plus 4yz squared in the z hat direction. So we're supposed to check Stokes' theorem, or the fundamental theorem for curls. So I take the curl of this. I can take the determinant of use the determinant method to calculate this curl, or I can just look and see what Griffiths does, and I'm just going to take that result. That result is that the curl is 4z squared minus 2x in the x hat direction plus 2z in the z hat. And now we need to figure out what our infinitesimal area vector is going to be. All right. So I think we can justify the magnitude fairly easily. The magnitude, since this is a piece of some surface, that surface lives in the yz plane, the magnitude is going to be dy dz. Now I have a direction we need to figure out. So previously we had defined the direction for an infinitesimal unit vector, an infinitesimal vector, surface vector, to be pointed outwards. All right. You can't define what outwards means in a case like this because this is a flat plane. But we're going to use the right-hand rule to pick a consistent direction for our choice of our surface vector. All right. So because I'm going to do my path integral in the counterclockwise direction, I'm going to use the right-hand rule, curl my fingers in the counterclockwise direction, and let my thumb tell me which direction I'm going to call my infinitesimal surface vector. Okay, so if I do that, I end up with something in the x hat direction. All right, I do that integral. I'll let you do that for yourself. You end up getting that over this surface, I think I forgot to tell you, it goes from 0 to 1 and 0 to 1, but you can look at your textbook. I add up all of those curls for that area, and I get 4/3. And now what I need to do here is then do the other side of my fundamental theorem for curls. So I need to evaluate over my closed perimeter the dot product of my field with my infinitesimal length, dl. Okay. But just like we did in the past, we need to make sure that we break this up into components, because over the bottom part of this path, dl looks very different than on the sides or the top. All right, so what we'll need to do is go ahead and choose dl, or choose different regions of our path that have a constant functional form for my infinitesimal length dl. All right, so in the end, we're going to have 4 integrals: an integral over the top, the left, the bottom, and the right. And what do you think that total should be if I add up all of those 4 components?